Welcome back to Codex. Our speaker today is Stefan Steinerberger, who is a professor at the University of Washington. Professor Steinerberger studies a wide variety of research problems using tools from PDEs, spectral theory, and harmonic analysis. Today, he'll talk to us about conformally rigid graphs. Take it away, Stefan.
All right. Thank you so much for having me. It's great to be here because most people in the audience know what a frame is. So this takes care of like 17 of my problems when explaining this. But I'll start sort of slowly, and I'll try to give sort of a reason why I'm interested in the thing that I'll tell you about. And I'll start sort of with sort of a pure analysis question. Suppose we've got some nice compact manifold, but assume the sphere or the torus or something close to a sphere. And we're given a nice real valued function on it. Can this expression be small? So it's the ratio of the gradients in L2 and the function L2. And the answer is yes, it can be very small, big constants. Okay. Well, what if you say, okay, constants don't count? You assume that you require your function to also have mean value 0. Can then this thing be small? Well, it's a good question. You can start looking at it. And the answer will depend on the manifold, right? This is a number that only depends on the manifold. And you start computing, and you take the sphere, and you realize it's not particularly small. You take the torus, you realize it's not particularly small. It's a number you can compute. But it can be small. So what property of the manifold makes it small? And there's a very nice picture I found, which from sort of an older paper. This is the famous dumbbell example. So you sort of have two balls, and they're glued together by a very thin bridge. And there's a very nice argument that, as far as I can tell, is not written down anywhere. So I'm ascribing this to Calabi. I might be incorrect. I'll show you but I'll give you the argument. The argument is what you can do is you look at the heat equation. And you look at the L2 norm of the solution of the heat equation, you apply the PDE, and you get this very nice relationship for the rate of change. So you start with some initial function on your manifold, the heat equation moves it around. And for example, first of all, you see the heat equation makes it smaller in L2 because there's a minus, the square here. But now there's a very simple trick. If this number lambda 2 exists, right, then it gives me an inequality, and the inequality is this. By definition, lambda 2 is the largest number for which this is true. So, this is true. So I can plug this back in, and I realize that the rate of change of the L2 norm of the heat equation can be written as this sort of very basic object. It can be written as proportional to itself. And that brings us back to the first class in ODEs, because it tells us that the speed with which, the rate of change or the evolution of the L2 norm of a solution of the heat equation can be written using exponential decay. Right? This is the ODE. Okay, it's maybe a Grunwald lemma, but it's basic ODE theory, and it tells us with exponential decay. And this tells us something about lambda 2. And at least that's what Calabi, I think, claimed. So if lambda 2 is very, very large, it means all solutions of the heat equation go to 0 pretty quickly. If lambda 2 is very, very small, it means there is at least one solution of the heat equation that goes to 0, still exponentially, but maybe very slowly. And this is in some sense insulation, right? it's getting colder again, right? I have to pay a heating bill. I want lambda 2 to be very, very small. And how do I do this? By having insulation in the walls. Insulation gives me small lambda 2, and you could also think of this bridge here as like, here's the inside of the house and here's the outside, and you make the actual interface small by insulating your walls. And in fact, if you now imagine that you look at a function that's -1 on the left side and +1 on the right side, then the heat equation would actually decay very slowly, because they can only meet in the middle, and they meet in a very small area, so they don't cancel very quickly. So Giga, who ascribes this argument to Calabi in the celebrated paper, he gives a more direct computation. He says, hey, if you've got a manifold like this, just put +1, -1 on the two sides, do a smooth interpolation in the bridge. And what you get is you just get a basic bound on the eigenvalue. Don't read this. It's just giving you a sort of this is basically a calculus kind of question. So you can do these computations. But what Chica says is, maybe the last sentence is relevant. It shows that in order to understand lambda, you don't need the volume or the diameter of the manifold are not enough. Something else is relevant. And what's relevant is the existence of bottlenecks, as in the example of the dumbbell, where you have a very thin connection between two regions. And so he's introducing the following quantity. He says you take all possible subsets of the manifold, and you minimize a ratio, and the ratio is the size of the boundary over the volume. So you want something that's very, very large on the manifold, but has a very small boundary. And if you look back at the dumbbell, you realize, oh yeah, this I can actually do. You take the left side of the dumbbell, it's a huge area, it's half the manifold, but the boundary is actually a very thin ring in the middle. So this is when H would be small. And it turns out there's a very nice inequality connecting these two things. And that's Chica's inequality, and that has been very impactful, let's say. So lambda 2 is an important object. It's connected to geometry. And this inequality, I like it because it's interesting in two ways. It's as if some inequalities are only interesting in one way, but here it's interesting both ways. If you have a large H, a large sort of isoperimetric coefficient, if every large set has to have a large boundary, then lambda 2 is also large. Conversely, if lambda 2 is small, then H has to be small, which means there has to be some sort of bottleneck along these lines, which is nice. Okay, now let's move to graphs. It turns out when you move to graphs, not much changes. You can think of this graph up there as a sort of a discrete version of the dumbbell example. And then all of this has been, you can define it, for example, like this. There's various different notions of graph Laplacians, but you can define it as of this very simple quadratic form. And then the same theory sort of carries on. And in fact, this has been used. Again, I guess people attending this talk are probably no stranger to spectral clustering, but I like the pictures, so I'll just show you one example. So it's kind of useful. So I'll give you an example. So what you do is you find solutions of the heat equation that go to zero very slowly. If they do that, then they're probably constant on one cluster and constant on the other cluster, and the interface is small, and that's why they go to zero slowly. So let's do an example. Here's the graph. We can see the two clusters with the eyes, right? We see there's a left one, there's a right one. But suppose I only give you the adjacency matrix. Well, I can still see it, right? There's a left block that's tightly connected. There's a right block. And then the across connections are very few, right? It's very sparse. But of course, this is cheating because this is presupposing I already know the solution. What you're given in practice is you're given a permutation. You don't know the labels of here the left block happens to be the first 50, and the next 50 are the right block. Yeah, then I've already solved the problem. So in practice, you get a permutation, right? Like this. So given this, how do you find out what's on the left and what's on the right? That's the question. And what you do is you just compute the first eigenvector of the graph Laplacian. This is the solution of the heat equation that goes to zero the slowest, and you get this very nice clustering, and it happens to give you everything you want. So this is very nice. Okay, just sort of a flavor of why these things are nice. Okay, so summary, if I understand, lambda 2 is tightly connected to the structure of the graph. It's tightly connected to bottlenecks. It's tightly connected to spread of information or heat. Lambda 2 being large means that there's a strong connectedness. Lambda 2 being small means there are bottlenecks. Okay, small deviation because I love it. What's the little f actually look like that minimizes this? If I look at the optimal heat distribution, the solution of the heat equation that goes to zero the slowest, what does that look like? And there is a tantalizing conjecture. It's the only way to call it. Tantalizing, it's terrible. It says if you're in a nice enough domain, then the maximum and the minimum are on the boundary. So I'll give you an example here. This is a domain. And on this domain, you see the solution of the heat equation. So the profile of the solution of the heat equation that goes to zero the slowest. And essentially what you have is you have negative values here and you have positive values here. The red and blue is not quite consistent with that. So red is cold and blue is hot. Sorry about that. And you see this profile, and what happens is you see these nice level curves, and here's the minimum and here's the maximum. They're both sort of on the boundary. And this you can do for many examples. But it's not always true. And here's the first counted example, maybe it's the second counted example. If the domain is very, very complicated, it can actually be that maximum and minimum are inside. Very annoying. We don't. This was even a polymath project a couple of years back, and I think, it's very difficult to make progress here. Question is, what do you need? And people widely believe that if the domain is convex, it's true. Everyone sort of believes this. In 2 dimensions, some people believe that simply connected is enough. Like if it's just simply connected, no matter what shape it is, maybe this is true. I'll tell you a theorem that I thought was 2 theorems that are hilarious. I proved it up to a constant, but the constant is not small. So if you have a long elongated domain, there's a relatively easy argument that shows that the maximum and the minimum are within 1 in radius or 2 in radii of the 2 points that are furthest distance from each other. There's not necessarily the boundary, but at least far away from each other. And I've tried very hard to make this, to make the constant smaller, preferably 0, but that doesn't quite work. And the other thing is that hotspots, in a funny way, is almost always almost true. So you could introduce a coefficient, and the coefficient looks as follows. You look at the maximum inside, and you look at the maximum on the boundary. And if it is true that the maximum is always on a boundary, then alpha is always at most 1. Now, we've already seen a counterexample to this, so alpha can be larger than 1. But it turns out in all domains and all dimensions, it can never be larger than 60. And this has since been improved to 6. And the best known lower bound, based on high precision numerics by Andreas Kleefeld, is 1.001. So hotspots, that's the most 1. Hotspots is false. That's a very famous annals paper from Lutzi and Werner from 22 years ago, 23 years ago. But it may be almost true up to like 1% in this sense. It's very funny. So Andreas tried very hard to actually get the constant up, and that's what he got. And there's even indication that in higher dimensions, the constant is even closer to 1. The proofs actually get stronger in higher dimensions. So the worst case might be 2 dimensions, and it may just be 1% off. Okay, this is just because I love hotspots. Okay, so what do we have is we've got graphs. When we have graphs, we can define heat equations. We can define eigenvalues of Laplacian matrices, and lambda 2, which is also known as the algebraic connectivity. It measures how easy it is to divide the graph into sort of 2 parts that have very few edges between them. That's it. And you can do all of this with weighted graphs, right? There's no difficulty here. So if you want to do weighted graphs, you just put a little weight here. And then there are versions where you put the weight down here as well, or a sum of the weights, but let's not worry about this. Okay, questions so far? Very good. So if this is really just vague motivation. So here's a question. This is lambda 2 on a graph. And now, okay, the main question that I want you to keep in mind is, what is the best structure for a computer network? So you have 17 computers. They're all connected, but then they're not all connected, right? Some of them are connected by wires. You get a computer network. What is the best connected network? Well, the easiest way to do it is you go out and you buy a whole bunch of cables and you connect every computer to every other computer. That's going to give you a really nice connected, highly connected network, right? That's great. But suppose you don't want to buy new cables, and maybe you don't want to dig holes and put new cables. You have the existing cables. Can you put some more emphasis on some of the existing cables, take some of the emphasis off of some of the cables? Can you shift the weights here around in such a way to make lambda 2 bigger? I argue that this is a very nice question, and it's an easy argument to make because I'm not the one making it. So there's actually prior work from maybe 15 years ago that deals with exactly this and how to compute the weights and how it becomes a semi-definite programming. There's some very nice math showing up.
Are you somehow forced to not change the current weights too much, or can you just erase all the weights and make an expander?
Right. No. So yeah, right. Oh, that's an excellent question. So you cannot make any new edges. You're restricted. The edges you have. because those are like the cables in the ground that they've already been dug, right? That you cannot dig any new holes. You cannot get new cables into the ground. You could set some of the existing cables to be weight 0, so you could just remove them. But you can't just expand, right? Otherwise, yeah, you build an expander. That's not allowed. So you're constrained to be within the existing network. But you can put additional sort of cables into the underground cable network. Oh, I mean, of course, you know, you need to normalize sort of the sum of the weights. Otherwise, if you just make, if you make the weights bigger, lambda 2 goes up, right? It corresponds to having more cables, and that gives you a better network. That makes sense. So assuming that you have a total capacity of cables that you're allowed to put in the ground, what's the best way?
If you were using the normalized Laplacian, would you be able to get rid of that second constraint?
So I'll be honest, we never looked at the normalized Laplacian because we looked at the standard Kirchhoff Laplacian, and then we ran into like 6 months of stuff. And by the end, we didn't quite have, I guess, the energy to start again. Also, the normalized one is more nonlinear, right? Like there's a d minus 1. I mean, you mean the d minus 1a or the d minus 1/2 a d minus 1/2?
I was thinking the symmetric normalization, but yeah.
Yeah, so the problem, right, so it gets extremely tricky. And the reason is the following. We're doing d minus a essentially with weights, which means that if I change the weights, they enter sort of linearly into the matrix d minus a. And I can do very beautiful semi-definite programming. If you do the normalized Laplacian or the random walk Laplacian, you have products of matrices, right? You have d to the minus 1a or d to the minus 1/2, a d to the minus 1/2, or I minus that. And then the weights end up being nonlinear, right? The entries in the actual matrix that you get are nonlinear. I mean, they're polynomial, but they're nonlinear functions of the weight. And then how do you even optimize this? And the reason we sort of followed this path is we could set up semi-definite programming. We could look at some simple examples. That simple examples would then lead to some theory and inspire some of our theorems. So as far as I know, the normalized one might be extremely interesting because it's so natural, right? As you said, right?
But the bottom eigenvalue is still going to be 0, right? So
we don't worry about 0.
He's asking about the second constraint. That's to keep you in the orthogonal complement of the kernel, right?
I thought he meant the weights.
Yeah, I meant that constraint. Yeah, no, certainly, yeah. The function that's constantly 0 is not very interesting, except for when it is. I meant the constraint on the weights.
Right. So yeah, no. So there's a version where you look at the normalization differently, and we just ran into such computational problems we couldn't even do even simple examples we couldn't do. Because you need to solve sort of a semi-definite programming, but then you need to find out constrain the solution to lie on like the image of certain polynomial equations. I mean, it became, even that was computationally kind of tough, actually. But great question. And in terms of content, I can't tell you. And now you know why, because we ran into these computational obstacles. Okay. So at some point, Rekha Thomas, who's my colleague, and we went for lunch. And we both like sort of eigenvalues and stuff. So we ended up chatting about, well, we ran into sort of a very simple question. And this is, okay, for each graph, you can do the computations and you get the optimal weight assignment. Which graphs have the property that the optimal weight assignment is constant? Constant weight. So it's just the graph itself. The graph itself is already the most perfect computer network you could imagine. You don't need to fiddle with weights. Fiddling with weights cannot help you. That's the question. And these are, we call them conformally rigid for reasons that will become clear in the next 2 slides. I'm sorry, this is a handful, but really this is lambda 2, right? It says you take lambda 2, you maximize it over all possible weight assignments. And the solution, maximizing lambda 2, the largest possible lambda 2, the most connected lambda 2, is attained if the weights are all constant. And then likewise, lambda n, the largest possible eigenvalue of the quadratic form, is minimized also by constant weights. And if a graph has these 2 properties, then we say the graph is conformally rigid. So, this looks maybe, why would we care about this? Let me give you some motivation. right? Why is it interesting? So here's sort of a frame-bound argument, right? So suppose we're given a list of numbers, and we're trying to compute the L2 norm of the vector, right? The sum of the squares. Okay, that's pretty easy. Now, a malicious spirit comes and gives us only differences. If I'm only given the differences, can I then compute the size of the vector? And the answer is no, because there's a symmetry. Of course, I can shift all the entries by a constant, and the constant gets annihilated by the differences. So I can only hope to recover things up to a constant. This is all I can hope to do. But it turns out that's the only obstruction. So if we assume that the sum of the xi's is 0, if we factor out the constant, then you do a little bit of algebra that's not very difficult, and you realize if you sum up all the differences squared, you get exactly a proportional number of the L2. You can see how the frame would come in, right? So now suppose we're not given access to all differences, but we're given access to some differences. Right? Because life is not perfect. Well, if I'm only given access to some differences, depending on what they are, I may be able to reconstruct everything. But in terms of the existence of such identities, what happens is there's a quadratic form bound, and that's just the fact that matrices are bounded from below by the smallest and the largest eigenvalue, right? Again, constrained to being mean value 0. So lambda 2 is not a lower frame bound, right? Lambda n is the upper frame bound, and we want the ratio to be as small as possible. And now one way to argue is, well, if I'm given all these differences, I could try to make my life better by introducing weights in my computation. Maybe that will make the ratio of lambda n over lambda 2 smaller. Maybe it gives me more accurate information. And now you could see conformally rigid graphs in this framework as structures where weights don't help. The information is already so balanced that you can't gain anything. Okay, that's maybe a frame-bound motivation. Here's a spectral geometry question for people who like sort of eigenvalues and PDEs. When you have a manifold, what you can do is you can sort of blow up parts of it in a way that the metric locally doesn't change in terms of angles. So if you've got two geodesics and they cross and you blow up the region like a balloon, right? Then the angles don't change. They stay the same. So these are called conformal changes, and it's very easy. You have a metric and you just multiply it locally with a non-negative function that corresponds to sort of blowing up or blowing down parts of the manifold. And here's an example. It's kind of funny. So you have this orc or maybe elf. It's really hard to say what that is on the left. And then this is a deformation in the middle, and on the right you see it's a deformation that locally preserves angles, and you see it by the fact that all the little circles remain circles. Well, not quite, but that's how it's illustrated here. So these are studied, and what happens is there's a very nice paper from 1970, which you don't have to read, but the interesting part is somewhere over here, where essentially, instead of proving a statement about the sphere, Hirsch is proving a statement about the sphere equipped with a weight, and then the final result is independent of the weight. So French aside, what people have since done is the following. You're given a manifold. You're trying to understand its, say, second eigenvalue. And you're allowed to do the following. You're allowed to blow up or blow down certain parts of the manifold. You're allowed to sort of, you're not allowed to change its shape per se, but you can put more weight here or there. And when you change the weight, there's a natural scaling, which is compensated by the volume term. And Hirsch's result can then be stated as follows. The second eigenvalue of the sphere as a manifold is maximized by the constant metric. So what happens is, in some sense, that the sphere is the most symmetric version of itself, which makes sense, right? It's the sphere. You can't hope to make it more symmetric by increasing or decreasing the volume in certain regions. Very vague formulation, very vague, right? Here's a historical formulation. So I'm very excited to mention this theorem, which I like very much. So first, a fun story. So apparently, at some point when Hilbert was pretty old, people were trying to give him like a collected works as a birthday present. And they found out that the papers were all wrong. So the theorems were always correct, and the proofs were all wrong, but they were wrong in a way that was fixable. And they hired Olga Taussky-Todd, who was unemployed at the time, and she spent 3 years of her life fixing all the mistakes in all of Hilbert's papers. And it turns out everything was correct except a proof of the continuum hypothesis. That turned out to be false. And then they gave the wonderful collected works to Hilbert, and apparently he didn't notice a single thing. And then Olga Taussky-Todd moved to the US, and she became sort of one of the founding mothers, I guess, of matrix theory. She was at Caltech for a long time. She was at NIST. And there's one particularly beautiful, oh, by the way, okay, this is funny. Her husband is involved in ensuring that Oberwolfach is not destroyed in 1945 or something like this. Like part of Oberwolfach, if you've been in the library, is actually named after Todd. And there's even various stories of him trying to like ensure cars don't get stolen. I would need to check the details. Anyway, here's a wonderful inequality. Okay, and that's by Fan Taussky-Todd. So you're given n+1 real numbers, and you should think of them as being arranged on a circle. So it's really n numbers arranged in a circular fashion, mean value 0, periodic. And then what happens is this very nice Wirtinger type inequality, it's called. It says that if you only know the differences between two adjacent numbers, if the numbers themselves are large, some of the differences also have to be large. And for people who like, discrete cosine transforms, this is really just, the proof is really just eigenvalues of the 2 minus 1 minus 1 tridiagonal matrix. If you write it out correctly, the smallest eigenvalue of that is given by this. So it's really eigenvalue computation. But simultaneously, it says, in some sense, you could turn it, you could go to math physics and say for the natural Schrödinger operator on the discrete circle, the ground state is given by sines and cosines. So it turns out the minimizing xi's are in fact discrete sines and cosines. So a very nice inequality. So he could now argue, maybe we can improve the constant if we introduce weights. And the answer is no. So this is the third motivation. We'll prove that cycle graphs are conformally rigid. And what this means is the following. You can't improve that constant even if you introduce weights here. So for every possible choice of weights, there is a choice of xi for which this thing is not strictly larger than what you'd get if all the weights were the same. Okay, so that's maybe the third reason. I mean, the big reason is we're just interested in what these graphs look like. Of course, they're connected to various parts of mathematics, but we were kind of interested. So again, the definition, we have networks. We have sort of the minimum connectivity. We have sort of the maximum connectivity. And we're interested in graphs where you can't improve on the graph itself. And sort of in analogy to the Hirsch result, these would be highly symmetric graphs. They would be the most symmetric version of themselves. Maybe that's too poetic, but okay, so the big question is, do they exist? Right. Okay, so yes, they do exist. And the thing that we found very puzzling is they seem to be complicated. They seem to be all sorts of interesting things. So here we see 3 conformally rigid graphs. The left is the Hoffman graph. I'll tell you a little bit about that later, which is very nice and symmetric and pretty. The middle one is the complement of the Srikande graph. I did not know about the Srikande graph or its complement before. The right is the smallest way to arrange 20, so the best way to arrange 20 vertices, where each one has degree 3, to have the minimum amount of crossings. If you write a graph in the plane, you can write it, maybe it's planar, then you can draw it without crossings. But if there's enough edges, there's going to be some crossings. And then the question is, okay, if you fix the number of vertices, which is 20, you fix the number of edges by requiring that it's cubic. So that would be something like 30. What's the minimum amount of crossings? And this graph realizes it. And it turns out to be conformally rigid. I mean, this graph only shows up in the literature once, in one paper, as far as I can tell. Like, it doesn't have a lot of structure, but it is conformally rigid. Okay, let me tell you sort of how we walked through this. I'll give you a very sort of elementary, I'll give you a hand-wavy proof of the cycle graph. Suppose this, don't read the statement. Look at my hands, okay? So we got this beautiful ring. Now, suppose we could put weights on the ring so that the eigenvalue of the associated matrix goes up. Okay, that could be, right? Now, then what happens is I could take all this magic weight arrangement and I could rotate it. And nothing would change, right? Because it's a rotation symmetry of the circle, nothing changes. I do this, the same eigenvalue shows up, the eigenvector gets rotated, right? But nothing else changes. Now I could do this n times. I get n different weight arrangements that all give me matrices with a large minimal eigenvalue. Okay. And then what you do is you sum them up. And by summing them up, you take an average, you produce something that's in the average greater than what each individual should be, and that's a contradiction. So I wrote this somewhere here. So it's not too shocking. You know, the cycle graph itself is already the most symmetric version of itself. Makes sense, right? Because adding weights should not increase this. There's a natural, beautiful symmetry here. Questions on the hand-wavy argument?
Could I ask oh, sorry. Okay.
Nice to see you.
Hey, a general question, which is there a way, if I just give you a graph and I say, I claim this is conformally rigid, is there a way to test or certify or something like efficiently?
Great question. I'll give you the 1 minute answer because I want to give you the 5 minute answer, but I can't. So here's the 1 minute answer. It all turns into a semi-definite program, which you then plug into Mathematica. What happens is the following. Mathematica will then say, oh, here's the solution of the semi-definite program. Here's the duality gap. And unfortunately, it will say the duality gap is 10 to the minus 9. Now, if Mathematica tells me something is 10 to the minus 9, I know it's 0. I know I've found a solution of the semi-definite program. This gives me a certificate that the graph is in fact conformally rigid. If it is not conformally rigid, it will say, hey, the duality gap is like, you know, this and this. And it will, so proving that something is not conformally rigid in practice is very easy. Rigorously proving that something is conformally rigid it can be an absolute nightmare. So at least half of our paper is just dedicated to strategies that we had for finding certificates. In many cases, we produce numerical certificates, and then we have sort of massaging techniques to turn them into symbolic certificates so that the 10 to the minus 9 becomes a 0. But we don't have yeah, I mean, you need to solve a semi-definite program in closed form sort of symbolically to do it right now. We don't have a better way.
And so if you have, like for the case of the cycle or something, if you have symmetry, I assume you can, that is inherited by the SDP, right? And you can reduce and... Even
better. Now I'm going to slide over.
Okay.
I'm not interrupting you. No, your question is great. So it turns out the argument we just had with the cycle and the rotation, you can actually carry over to edge transitive graphs, which are graphs where there's one element in the automorphism group where every edge is in the orbit, which is just a technical way of saying the same argument works. So it turns out edge transitive graphs are conformally rigid, and that's a proof. And this covers complete graphs, it covers cycles, complete bipartite graphs, hypercubes. You know, there's many edge transitive graphs. And this is not a complicated proof. You can prove this. Wait, other questions? Because now I interrupted you to like show the next slide. Maybe not. Oh, okay. Well, we can talk later. But okay, so this is what we have right now. Then the second one, and maybe combinatorially most exhausting statement is distance regular graphs. What is distance regular? It means that if you take two vertices and you say how many are distance 5 from the first and distance 3 from the second, and you know that those two themselves are distance 17 from each other, then you can answer the question without knowing which of the two vertices you picked. So it's just a function of the distance of the two vertices and the distances from each that you want. These, you know, if people who know coding theory, I guess, are no strangers to distance regular graphs. It turns out those are also conformally rigid. I'm not going to give you the proof because that's a lot of SDP theory and external magic. So it turns out that there's a theorem that we can prove, and I'm not going to go into this, but there's a theorem where you can characterize conformal rigidity by the ability to embed the vertices of the graph into the eigenspace of the second or the largest eigenvalue in such a way that everything that's connected by an edge ends up being distance 1 or a fixed distance, universal distance from each other. So it's an edge isometric embedding of the vertices into the eigenspace. If that exists, then you're conformally rigid. And it turns out there's structure theory for distance regular graphs, going back to Godsell, that says you can do this if the graph is distance regular. So then we just like the result and we're done. And this theorem essentially is duality theory for STPs, and that's where Rekha's the real expert, so I will not say too much maybe. Okay, so this is regular. This gives us the following picture. So we have edge transitive gives us conformally rigid. Distance regular gives us conformally rigid. And there's a whole bunch of other graphs that I'm not going to explain here that lead to one of the two. So we sort of have an, we know that some families are not conformally rigid. Okay, next natural example. Cayley graphs, right? So you take some nice finite group, finite number of elements. You take a bunch of elements to be the generators. And then the vertices are just the elements in the group. And you draw edges between G and S applied to G for all G and S of G, right? So this is how you create the edge structure. And we want undirected edges, so we want the symmetry in the generators. So it turns out they can be conformally rigid, but they need not be. There's no clear-cut answer here. Left, you see the smallest Cayley graph that is not conformally rigid. So in fact, if you weaken the edge connection between the inner and the outer triangle, you can make the eigenvalue a little bit bigger, turns out. And on the right, you see a Cayley graph on Z18. And that is conformally rigid, but it's not edge transitive, right? So it's kind of outside the existing class that we had. And we have a pretty nice theorem. Well, we almost have a characterization. So here's the statement. I'll just write it down. If you give me such a Cayley graph, the following happens. If I can find an eigenvector in the second eigenspace such that this magic sum is the same number for all generators, and if you can also do this with the largest eigenspace, then the graph is conformally rigid. It's actually a very nice argument that uses very basic properties of Cayley graphs. So it's a necessary condition. Sorry, it's a sufficient condition. Sufficient. It's probably also necessary. That's why it's kind of annoying. So in practice, this is a nightmare. So if you give me a Cayley graph and the multiplicity of the second eigenspace is 1, I'll just check it out. That's easy. I apply this thing. It works or it doesn't work. The moment the eigenspace is high multiplicity, I have to kind of check all possible elements in that high dimensional eigenspace whether it satisfies this. And usually it's only one that does satisfy it. So it's not really a useful criterion. But we are inclined to believe, let me not call it a conjecture, but we're inclined to believe that it actually characterizes Cayley graphs that are conformally rigid. Okay. Questions so far?
What does a dotted arrow mean?
Well, it's complicated.
Cool.
Well, you apply the previous theorem, and maybe that tells you the story. It can or it cannot be, right? But we know a little bit about it.
So arc transitive is conformally rigid because it's vertex and edge transitive and therefore edge transitive?
Yes.
Cool.
That's it. So, okay, now it gets funny. It should get funny at the end, right? So, in the beginning, we kind of hoped to get a nice characterization, and at some point we ended up here. And we're kind of hopeful that this is kind of it. You see the Cayley graph result is incomplete, or maybe the converse is also false, right? I mean, that I don't know. But Mathematica has this beautiful library of 12,000 graphs. So you just run a for loop. Okay, we didn't do all 12,000 because checking STPs becomes really tricky when they get large, right? So we did up to like size 100. And we looked for graphs that are not in this class, but conformally rigid. Could be, right? Maybe we missed something. And that's in fact how we first discovered stuff, right? So in the edge transitive case, the circles, we just sort of did by paper, right? It's clear that this has to be true. Then we went through the Mathematica library, said which ones are conformally rigid, but not edge transitive. We found distance regulars. Okay, that was a lot of work proving that. Then we said Cayley has to be true, and in fact, there's a lot of Cayleys that are conformally rigid, like a lot. But that led to that result. So the question is now, what remains? Right? So I will say on a meta level, it appears to us that this is kind of the complete picture, except there's a list of 8 sporadic outliers, and maybe many more, but there's at least 8. So these graphs are conformally rigid, but they're not edge transitive. They're not distance regular, and they're not Cayley, I think. So I think we've made sure that they're not Cayley.
What graph library did you pluck these out of?
Mathematica.
And what's the size of the largest graph here? It's like 48.
So after we put the paper on the archive, we got an email by Weinstein, who said the 120 Klein graph also works. So now it's 9. It becomes just very hard to check because it's a function of the number of edges. So the number of edges is the number of variables in your SDP. If you've got like 5,000 variables, you can't really do it on the laptop anymore, right? So I just want to show you 3 of these graphs, these exceptional outliers, because I'm kind of shocked by the non-uniformity. I'm going to show you the following 3. Hoffman graph, gorgeous, known since the 60s, very famous, 16 vertices, same girth, graph diameter, graph spectrum, characteristic polynomial as the hypercube graph in 4 dimensions. So spectrally indistinguishable from it, but I think smaller radius and just very beautiful and fundamental and shows up everywhere. It's a gorgeous graph. Okay. Also it's the smallest counterexample we have that doesn't fall into the category. We were very happy to see this one. That's a great graph. Yeah, this is the smallest 3 regular graph that has crossing number 6. So if you draw a graph with 20 vertices and each vertex has degree 3 in the plane in such a way that you only have 6 crossings, you see there's a crossing here, and there's one here, and there's one here. What am I missing? Oh, there's one here, there's one here. Okay, there we go. Then there's 3 solutions, and this is the second one. And as far as we can tell, it shows up in the literature exactly once. Yeah. That's the only paper that has this graph. It's not a famous graph. It's not well known. But it is conformally rigid, which is really hard to do. And the last one is defined. It's 2 years old. It's kind of, it's a circle, and then you have 2 going forward or 2 going back in like an alternating fashion. It's called accordion graphs because you kind of imagine playing the accordion with them, right? If you draw them differently. What's special about them? We don't know. There's a lot of accordion graphs, a lot of parameters, but this is the one that's conformally rigid. We don't know why. Some special kind of magic showing up. Okay, now I think I have appropriately shared my excitement and confusion. And thank you very much.
All right, let's thank the speaker by clicking buttons. I'll stop the recording here.